Curious about what makes your computer tick? Let's dive in. Computer science is the secret sauce behind your favorite gadgets, from algorithms that sort your photos to AI that suggests your next binge watch. Think of the CPU as the brain and software as the brain's instructions. Logic gates? They're like tiny decision makers inside. All this tech wizardry translates binary code into everything you see and do. So next time you fire up your computer, thank computer science for the magic. See? Told you it's cool. Computer science is the study of computers, computational systems, and their theoretical and practical applications. It encompasses a broad range of disciplines, including algorithms, data structures, software and hardware development, and artificial intelligence. Essentially, it's about understanding and applying the principles of computation to solve problems and create new technologies. Computer science deals with the fundamental processes of how information is processed and manipulated. These are step-by-step instructions that computers follow to solve problems. Computer science involves understanding how software, programs, and hardware, physical components, interact and function. Computer science also explores the theoretical underpinnings of computation, including concepts like the theory of computation and information theory. Computer science has a wide range of applications, from developing software and mobile apps to designing computer systems and even creating artificial intelligence. Some say computers make no sense. What the heck is going on here? Inside your PC is a central processing unit, or CPU. It's basically just a piece of silicon with billions of microscopic switches called transistors. Depending on the flow of electricity, they can be on or off, kind of like a light bulb, which gives us two states, 1 and 0. The value of one of these switches is called a bit. One bit by itself doesn't really do much, but put them together and magic starts to happen. A group of 8 bits is called a byte, and can binary have 256 different combinations of 0s and 1s. Congratulations! We can now store information by counting in a system called binary. Every bit represents a power of 2, 1 meaning the power is included and 0 meaning it's not. So this number has 1 times 64, 1 times 4, and 1 times 1, which adds up to 69. This is nice, but for humans, hexadecimal is hexadecimal even better. It's often denoted by this 0x and is simply a more readable format than binary. 4 binary bits can take any value from 0 to 15. Hexadecimal uses 0, 9, and AF to represent those values, so a group of 4 bits can be replaced by one hexadecimal digit. Okay, now that we can store numbers, we just need computers to actually, do something with them. Using transistors, you can make logic gates. In computing, hardware refers to the physical components of a computer system, like the monitor, keyboard, and CPU. Software, on the other hand, is the set of instructions that tell the hardware what to do, including operating systems and applications. Physical components, these are the tangible parts of a computer that can be seen and touched. Examples: CPU, memory, RAM, hard drive, graphics card, monitor, keyboard, mouse. Function, hardware provides the physical infrastructure for a computer system. Software is a set of programs or applications that provide instructions to the hardware. Operating systems like Windows or macOS, web browsers, word processors like Microsoft Word, and video games. Software allows users to interact with the computer and perform specific tasks. Logic gates are fundamental electronic devices that form the basis of digital circuits, including those found in computers. They are essentially switches that can be either on, 1, or off, 0, and they operate on these binary inputs to produce a specific output. Logic gates are the building blocks of digital circuits and are used to perform basic logical operations. They take one or more binary inputs, 0 or 1, and produce a single binary output. Logic gates implement Boolean logic, which deals with true-false statements and logical operations like AND, OR, NOT, NAND, NOR, and XOR. Common types of logic gates include AND, OR, NOT, NAND, NOR, XOR, and XNOR. Each type of logic gate has a specific truth table that defines the output for all possible input combinations. Logic gates can be combined to create more complex circuits that perform specific tasks. Logic gates are used in various digital devices, including computers, smartphones, and tablets. Logic gates, which are electronic circuits that encapsulate logical statements. You can think of it as a light bulb with 2 switches where the light only turns on under certain conditions. For example, only if A and B are on. By combining logic gates in a clever way, Boolean algebra, you can build circuits that perform calculations according to Boolean algebra, which is a system formalizing mathematical operations in binary. But even though computers understand 0s and 1s, ASCII for humans, it's not really all that useful. So, using a character encoding like ASCII, we can assign a binary number to each character. When you type an A on your keyboard, it gets translated into this binary code, and as soon as the computer sees this, it says, "Ah, yes, that is a capital A," and slaps it on the screen. How these devices fit together is handled by an operating system kernel like Windows, Linux, or Mac, which sits between computer hardware and applications and manages how they all work together, for example with device drivers. Machine code, also known as machine language or native code, is the elemental language of computers, consisting of binary digits, 0s and 1s, that the CPU understands and executes directly. It represents instructions for the computer to perform operations. Machine code uses binary numbers, 0s and 1s, to represent instructions and data. The CPU directly reads and interprets these binary sequences to perform operations. Machine code is the lowest level of programming, directly interacting with the computer's hardware. Each processor family, like x86 ARM, has its own unique instruction set and machine code. High-level programming languages like Python, C++ are translated into machine code by compilers or interpreters before execution. Machine code instructions can include operations like adding two numbers, moving data, or jumping to another part of the program. Assembly language is a low-level language that provides a human-readable representation of machine code instructions, making it easier to write and debug programs. Input devices allow you to give the computer instructions with the press of a button, but at the lowest level, computers only understand instructions in machine code, which is binary code telling the CPU what to do and which data to use. When it comes to following these instructions, the CPU is kind of like a genius, just with the memory of a demented goldfish. It can handle any instructions, but it cannot store any data RAM, so it's only really useful with random access memory or RAM. You can imagine it like a grid, where every box can hold one byte of information, which can be data or instructions, and has an address, so the CPU can access it in 4 steps. The fetch-execute cycle, also known as the fetch-decode-execute cycle, describes the fundamental process by which a CPU executes instructions. It involves fetching an instruction from memory, decoding it to understand what action it represents, and then executing that action. This cycle is repeated continuously until the program completes. The CPU retrieves an instruction from memory. This is done using the program counter, which holds the memory address of the next instruction to be executed. The address is then copied to the memory address register, MAR, and the instruction is retrieved from memory. The fetched instruction is then interpreted by the CPU's control unit. This involves understanding the type of operation the instruction represents, for example, add, subtract, move data, and identifying any necessary operands, data, or addresses that the instruction will act upon. The CPU carries out the decoded instruction. This might involve performing a calculation, for example, adding two numbers, moving data between registers and memory, or jumping to a new instruction. Once the instruction is executed, the program counter is typically incremented to point to the next instruction in memory, and the cycle starts over. Fetch from memory, decode instructions and data, and finally, execute and store the result. This is one machine cycle. Since a program is basically just a list of instructions in memory, to run it, the CPU executes them one by one in machine cycles until it's complete. Oh yeah, did I mention that this happens like really fast? In computer terminology, a CPU, or central processing unit, is the main component that executes instructions and performs calculations within a computer. It's often referred to as the brain of the computer because it controls the flow of data and carries out commands. The CPU fetches instructions from memory, decodes them, performs calculations or logical operations using its internal components like the arithmetic logic unit, ALU, and then sends the results back to memory. A CPU is a type of integrated circuit, specifically a microprocessor that contains the necessary circuitry for performing these tasks. CPUs can be single-core, multi-core, like dual-core, quad-core, or even more, or embedded processors, each with its own characteristics in terms of processing power and use cases. You'll find the CPU on the computer's motherboard, the main circuit board that connects all the hardware components. Modern CPUs can do billions of cycles every second, which are coordinated and synchronized by a clock generator. The speed of this clock is measured in GHz, and people often overclock their CPUs to improve performance, which is nice, but might just set your PC on fire. What's ever crazier, though, is that a CPU has multiple cores, which can all execute different instructions in parallel, so at the same time. Each core can be split into multiple threads, which also allows every single core to handle multiple instructions concurrently, so switch between them really quickly. Okay, that's cool, but it doesn't matter how powerful a computer is if you have no way to give it instructions in the first place. Typing machine code by hand would probably make you go insane, but luckily, you don't have to. Shell the kernel is wrapped in a shell, which is just a program that exposes the kernel to the user, allowing for simple instructions in a command line interface with text inputs. A programming language is a system of notation for writing computer programs. Programming languages are described in terms of their syntax, form, and semantics, meaning, usually defined by a formal language. Languages usually provide features such as a type system, variables, and mechanisms for error handling. An implementation of a programming language is required in order to execute programs, namely an interpreter or a compiler. An interpreter directly executes the source code, while a compiler produces an executable program. But the best way to make a computer do something useful is with a programming language, which uses abstraction, so that instead of this, you can write code that looks like this, which is then converted into machine code for you. Some languages like Python use an interpreter source code to machine code, which directly tries to execute the source code line by line. Other languages like C or Go use a compiler, which converts the entire program into machine code before putting it in a file the CPU can execute. Now, every programming language has different syntax, but there's some basic tools. Almost all of them have variables and data types. In programming, variables are containers for storing data, and data types specify the kind of data a variable can hold, such as numbers, text, or Booleans. Understanding variables and data types is crucial for writing programs that can process and manipulate information correctly. A variable is a name memory location that can store a value of a particular type. Variables allow you to store, access, and modify data within a program. Variables must be declared before they can be used, specifying their name and data type. Example: Python. Age = 30. Here, age is the variable, and it's assigned the integer value 30. The most basic way to use data is with variables, which assigns a value to a name, which can then be reused and modified. Depending on the value, variables can have different data types. For text, there's single characters and strings of multiple characters. For numbers, there's integers, which can also be signed if they're negative, and floating point numbers for decimal values. They're called floating point because the decimal point can float around to trade off precision with range. This is possible because they use scientific notation. It's some number times a power telling you where to put the decimal point, which is exactly what they look like under the hood. The actual number is stored with binary fractions. Some fractions, like 1/3, can only be approximated in binary with an infinite sum. But since memory is not infinite, you have to cut it off at some point, which leads to rounding errors, causing pretty weird calculations sometimes. If these are not enough, long and double use twice the amount of memory to double the range of integers and floats. 32-bit integers can hold values in the range -2,147,483,648 to 2,147,483,647. 32-bit floats can hold decimal numbers in the range +1.402398446E45 to +3.40282347E+38. In computers, numeric primitives are fundamental data types used to represent numbers. Their size is typically measured in bits or bytes, and they vary depending on the specific type and programming language. For example, a 32-bit integer, like int, can hold values in the range of approximately -2 billion to +2 billion. Floating point numbers like float, 32-bit, and double, 64-bit, have different sizes and ranges as they represent numbers with decimal points. Some languages like Python automatically figure out which type a variable is, but in a language like C, you have to explicitly declare the type of a variable. A data type determines the type of value a variable can hold, influencing how the value is stored and how operations can be performed on it. Numeric, int, integers; float, floating point numbers; double, double precision floating point numbers; text, str, strings, sequences of characters; Boolean, bool, representing true or false; other, char, single characters; array, collection of values; object, representing an entity. Example, Python, name =, Alice. Here, name is a variable of type str holding the string Alice. Is active =, true. Here, is active is a variable of type bool holding the Boolean value true. In computer programming, a pointer is a variable that stores the memory address of another variable or object. It allows you to access and manipulate data stored in memory directly, enabling efficient memory management and the creation of complex data structures. Every variable and object in memory has a unique address, a specific location in computer's memory. A pointer holds this memory address, acting as a reference to the location of the data. Pointers allow you to directly access and modify the data stored at the referenced memory location, passing data between functions efficiently by reference, creating dynamic data structures like linked lists, trees, and graphs, efficiently managing memory. Common in languages, pointers are prevalent in languages like C and C++, where they offer direct memory manipulation capabilities. Imagine a pointer as a label on a file in a filing cabinet. The label pointer points to the specific file's location, allowing you to easily find and access it. The value of a variable is stored at some address in memory. Pointers are variables whose value is the memory address of another variable, which is denoted by this ampersand. So really, a pointer is just some chunk of memory, pointing to another chunk of memory. Since a memory address is just a number, you can add and subtract from it to navigate through individual bytes of memory. This is called pointer arithmetic. In the context of computers, an application, often referred to as an app, is a software program designed to perform specific tasks directly for the user. These applications run within the operating system and are what we interact with to complete various activities. An application is a software package that executes a particular function or set of functions, either for a user or another application. Common examples include word processors like Microsoft Word, web browsers like Chrome, email clients like Outlook, image editors like Photoshop, and video players like VLC. Desktop versus mobile. Applications can be categorized as desktop applications for computers or mobile apps for smartphones and tablets. Applications are designed to help users with a wide range of tasks, from writing documents and managing files to browsing the web, communicating with others, and even playing games. Memory management in a computer is the process of controlling and coordinating the computer's main memory, ensuring efficient allocation and deallocation of memory to running programs and processes. It's a key function of the operating system, enabling multitasking and protecting system integrity. Assigning specific portions of memory to programs and processes that need to execute, releasing memory that is no longer needed by a program, making it available for other processes, keeping track of which memory locations are allocated and which are free, ensuring that memory is used efficiently and that multiple programs can run concurrently without interfering with each other. Efficiency allows multiple programs to run simultaneously, multitasking, without interfering with each other. Security prevents unauthorized access to memory by one program to another. Performance ensures that programs have the memory they need to execute efficiently. Resource management manages the limited amount of main memory in a computer system. Contiguous allocation, allocating memory in a continuous block. Non-contiguous allocation, allocating memory in non-continuous blocks, for example, using paging and segmentation. Paging, dividing memory into fixed-size blocks, pages, and managing them in a consistent way. Segmentation, dividing memory into logical segments of varying sizes. Virtual memory, a technique that uses hard disk space to extend the available RAM, allowing programs to run even if their total memory requirements exceed the available RAM. Swapping, moving data from RAM to disk and vice versa, to free up memory or to accommodate programs that don't fit in RAM. In some low-level languages like C, you have to manually allocate and free up memory once it's no longer used. This all happens in the heap, which is a part of memory that can dynamically grow and shrink as the program demands, which allows for more control but makes it incredibly easy to completely break your code. You could touch memory you're not supposed to, or that simply doesn't exist, which is known as a segmentation fault. But also, if there's some chunk of memory that's no longer used, and you forget to free it or you have no way to access it anymore, that memory is no longer usable. This is called a memory leak and will make the program slow down and eventually crash. To avoid this mess, high-level languages like Python have built-in garbage collectors that manage memory for you. Different data types take up a different amount of memory. Integers are most often 4 bytes of memory. A single character is most often 1 byte of memory, and a string is just multiple character bytes, with a NUL character to signal the end of the string. Storing multiple items in a contiguous chunk of memory like this is the idea of an array. More generally, it's a list type with the same data type, with each item having a numerical index, most often starting at 0. Since the items are next to each other in memory, by knowing the address of the first item, you can quickly index to any item in the array by using pointer arithmetic. Arrays are what's known as a data structure, which is just a way to organize data to make it easier to work with. Retrieving values from an array is blazingly fast, but the size of an array is often fixed when creating it, so when it's full, you can't add anything, and if you don't use all of it, it's just wasted memory, so a more flexible option is a linked list. In computer science, an array is a fundamental data structure that stores a collection of elements of the same data type, typically in contiguous memory locations. It's like a container that holds multiple values, allowing you to organize and access data efficiently. All elements within an array must be of the same data type. For example, all integers, all strings. Elements are stored in contiguous memory locations, meaning they are next to each other in memory. Each element in an array has an index, a numerical position. Allowing you to quickly access any an array is typically declared with a single variable name, which represents the entire collection of elements. Imagine you want to store the scores of 5 students in a class. You could use an array of integers to hold these scores. Each element in the array would represent the score of a specific student, and you could access the score of a particular student by using their index in the array. For example, score would be the score of the first student, score would be the score of the second student, and so on. Accessing elements by their index is very fast, O1 time complexity, making arrays suitable for tasks that require frequent data retrieval. Arrays allow you to organize related data under a single name, making it easier to manage and process. Because elements are stored contiguously, arrays can benefit from cache locality, which can improve performance. In summary, an array is a fundamental data structure that provides a simple and efficient way to store and access collections of data of the same type. A linked list is a linear data structure that stores a sequence of elements where each element, called a node, contains a data value and a pointer or link to the next node in the sequence. Unlike arrays, elements in a linked list are not stored in contiguous memory locations. Instead, they can be scattered throughout memory and the pointers connect them. Node. Each element in a linked list is a node consisting of data and a pointer to the next node. Pointer, link. The pointer in a node holds the memory address of the next node in the sequence. Head. The first node in the list is called the head. Tail. The last node in the list is called the tail. Each node has a pointer to the next node, allowing traversal in one direction forward. Each node has pointers to both the next and previous nodes, enabling traversal in both directions. The last node's pointer points back to the head, forming a circular structure. Advantages of linked lists. Linked lists can grow or shrink dynamically at runtime, unlike arrays which require a fixed size. Efficient insertion and deletion. Adding or removing elements in the middle of a linked list can be done efficiently by updating pointers without the need to shift elements like in arrays. Flexibility in memory. Allocation. Nodes can be stored in non-contiguous memory locations, making them suitable for situations where memory allocation needs to be dynamic. To access an element in a linked list, you must traverse the list from the head, which can be slow for large lists. Each node requires memory for the data and the pointer, potentially increasing memory usage compared to arrays. Searching for a specific element in a linked list requires traversing the list sequentially, which can be slow for large lists. Implementing stacks and queues. Linked lists can be used to create dynamic stacks and queues. Graph implementation. Linked lists can be used to represent the adjacency list of a graph. Dynamic memory allocation. Linked lists can be used for managing memory blocks efficiently. Undo-redo functionality. Linked lists can be used to implement undo and redo features in applications. It uses nodes containing a value and a pointer to the next node, which allows them to be spread apart in memory. Also, it can grow and shrink dynamically, as you can add and remove any node, and you can reorder it by simply rearranging the pointers. This is great, but they can be impractical, as you have no way to access the last node except if you traverse every single one before it. But still, both arrays and linked lists are useful, as they allow you to create queues and stacks. A stack follows the last in, first out principle, just like taking a pancake from a stack. Practically, just imagine a pointer that always points to the item that was last added to the structure. Then you can pop, so remove the last item, which increments the pointer back. A queue follows the first in, first out principle and uses two pointers, one for the first item that was added and one for the last. Any new item gets added after the last pointer, which is then updated, and dequeuing starts at the first pointer. Another useful data structure is a hash map. In computer science, both stacks and queues are fundamental linear data structures used to organize data in specific ways. Stacks follow the LIFO, last in, first out principle, meaning the last item added is the first one removed. Queues, on the other hand, follow the FIFO, first in, first out principle, where the first item added is the first one removed. Think of a stack of plates. The last plate you put on top is the first one you take off. Basic operations. Push adds an item to the top of the stack, and pop removes the top item. Undo, redo functionality in text editors, managing function calls, and evaluating expressions. Think of a line at a ticket counter. The first person in line is the first one served. onQueue adds an item to the rear of the queue, and dequeue removes an item from the front. Managing print jobs, handling requests in a server, and simulating real-world scenarios like call center queues. In essence, the key difference lies in the order in which items are added and removed. LIFO for stacks and FIFO for queues. Hash maps, which is just a collection of key-value pairs. It works kind of like an array, but uses a hash function to take a key and assign it to an index where its value is then stored. But sometimes two different keys can map to the same index, which is called a collision. There's different ways to deal with this, but one way is to create a linked list at that position in the array, which makes it a little slower to look up that value, but still, hash maps are incredibly useful because you can define the keys that point to every value, and since they're based on arrays, retrieving them is blazingly fast. For many problems, it can be very graphs useful to represent the relationship between different data points as a data structure. If you take the nodes of a linked list but allow any node to point to any other node, you get a graph where the nodes are connected by edges that can be directed, undirected, and can even carry a weight, which can stand for any metric, such as distance or cost. Graphs are useful for analyzing groups inside networks or finding the shortest path between 2 points, for example in Google Maps. There's two main ways to search a graph. Breadth first search starts at one node and moves out layer by layer until it finds the target node for the first time. Depth first search explores every single path fully until it reaches a dead end. Then it backtracks to the last node with a different path and continues from there in the same way until it finds the target node. A graph where any two nodes are connected by trees exactly one path is called a tree and represents a hierarchy, for example, the file system on your computer. A tree starts at the root and branches out into subtrees which end in leaf nodes. Parent nodes can have any number of child nodes, but oftentimes binary trees are the most useful. For example, a binary tree where all the values left of any node are smaller and all the values right of it are greater is called a binary search tree, which makes finding specific values super fast. If you want to find a target value, just start at the root. If the target is smaller than that node, go left. If it's greater, go right, and repeat this until you find the target. What we just used is a very simple algorithm, functions, which is just a set of instructions that solves a problem step by step. The simplest way to write an algorithm is in the form of a function. It takes inputs, does something with them, and returns an output. Just like variables, you can then call a function by its name and pass in different arguments. When calling a function, the function call gets pushed onto the call stack, which is short-term memory used for executing code, and as the name implies, it's based on the stack data structure, which means last in, first out. In the context of computers, computation refers to the process of carrying out calculations and processing information according to a defined set of rules known as algorithms. It involves using the computer's processing power, like the CPU, to perform various tasks, from simple arithmetic to complex problem solving. These are the step-by-step instructions that a computer follows to solve a problem or perform a task. They can be mathematical, logical, or based on other rules. The CPU is the main part of a computer that executes instructions and performs calculations. It's often referred to as the brain of the computer. Computation includes handling and manipulating data, which can be numbers, text, images, or other formats. Computers can be used to solve a wide range of problems, from simple mathematical equations to complex simulations or AI tasks. Adding two numbers, calculating the square root of a number, sorting a list, or even processing images are all examples of computation. In essence, computation is the heart of how computers work. It's the process of using the computer's hardware and software to perform tasks and solve problems based on well-defined instructions. To implement algorithms, you often have to compare two values, which you can do with operators like greater than or equality, and logical expressions such as and, Oregon, and not. Expressions like these are simple. They can be true or false, which are the possible values of the Boolean data type, and allow you to write conditional statements. If some condition is true, do this, else do that. Booleans can also be used to loop over certain parts of code. One way is with a while loop. While this condition is true, this code will execute. Another way is a for loop, which can iterate over every element inside a data structure like an array, but can also loop for a specific number of iterations by setting a starting value, incrementing it after each iteration, and setting an upper bound with a condition. In computer programming, Booleans are fundamental data types that represent logical values of true or false. Conditionals, like if, else, and elif, use Boolean expressions to determine which blocks of code to execute. Loops, like for and while, use Boolean expressions to control how many times a block of code repeats. Booleans are like binary switches, either on, true, or off, false. They represent the result of a comparison or logical operation, allowing programs to make decisions. Example: is raining =, true, or age? =18 evaluates to true or false. Conditionals allow a program to execute different code blocks based on whether a Boolean expression is true or false. Example: if is raining, print, bring an umbrella. Else, print, enjoy the sunshine. If, else, and elif statements are commonly used to create branching code execution. Loops allow a block of code to be executed repeatedly, typically based on a Boolean condition or counter. Example: while counter 10, print counter, counter ++, repeats until counter is no longer less than 10, for, and while loops are common types of loops. In computer science, recursion is a programming technique where a function calls itself either directly or indirectly to solve a problem. This process breaks down a complex problem into smaller, similar subproblems. Recursion often provides concise and elegant solutions for problems that have a natural recursive structure. Functions can also call themselves, which is known as recursion. This is useful when a problem can be broken down into smaller identical problems, such as calculating 5 factorials, which is just 5 times 4 factorial, which is just 4 times 3 factorial, and so on. But by default, a recursive function will just keep on calling itself forever. This means that it keeps pushing more function calls onto the call stack until the stack memory is exceeded in a stack overflow. To stop this, you have to add a base condition to a recursive function which defines when to stop. Only then will the function calls be executed without crashing your PC. Recursion is cool, but it can be pretty expensive time and space-wise. A function that calls itself is called a recursive function. Every recursive function must have a base case, which is a condition that stops the recursion and returns a value without further calls. Without a base case, recursion would continue indefinitely, leading to a stack overflow error, according to YouTube. The recursive case is where the function calls itself with a modified input, working towards the base case. Calculating the factorial of a number recursively involves defining the factorial of n as n, multiplied by the factorial of n1, with the base case being factorial 1 equals sine 1, as explained by IBM developer. Recursion is a powerful tool for solving problems that can be naturally decomposed into smaller, similar subproblems, making it suitable for tasks like traversing data structures like trees and graphs, or solving mathematical problems like finding factorials or Fibonacci sequences. So, to minimize the number of computations needed, past results can be saved in a cache. So if they come up again, the computer doesn't have to recompute them from scratch. This is called memorization. Speaking of performance, to judge how good an algorithm is, you can look at time and space complexity, so how much time or space is required to run it. In computing, memorization is a technique often used in programming where the results of expensive function calls are stored cached to avoid recomputing them when the same inputs occur again. It's a form of caching specifically for functions that take a while to execute. Memorization is a top-down approach in dynamic programming that stores the results of function calls in a table. When a function is called with a specific input, the result is first checked in the cache. If the result is already stored, it's returned directly, otherwise the function is executed and the result is stored in the cache for future use. Memorization is useful for optimizing code, especially when dealing with recursive functions or algorithms that involve repeated computations. By storing results, it can significantly reduce the execution time of the program, especially when the same inputs are used multiple times. Imagine a function that calculates the factorial of a number. If you memorize this function, the first time you calculate the factorial of 5, the result is stored. Then if you need the factorial of 5 again, you can just retrieve the result from the cache instead of recomputing it. Time complexity, often expressed using Big O notation, describes how an algorithm's runtime scales as the input size grows. It provides a way to understand the efficiency of an algorithm in terms of the number of operations it performs. Big O notation is used to classify algorithms by their growth rate, helping developers choose the most efficient algorithms for specific tasks. This refers to how the execution time of an algorithm increases as the input size increases. It's a way to measure how quickly an algorithm can solve a problem of a certain size. This mathematical notation is used to describe the upper bound of an algorithm's time complexity. It focuses on the dominant term in the runtime expression, ignoring constant factors and lower-order terms. For example, ON represents linear growth, while ON squared represents quadratic growth. O1, constant time. The algorithm's runtime doesn't change regardless of the input size, for example, accessing an element in an array by its index. O log n, logarithmic time. The runtime increases logarithmically with the input size, for example, binary search. On, linear time. The runtime increases linearly with the input size, for example, searching for an element in an unsorted list. On squared, quadratic time. The runtime increases proportionally to the square of the input size, for example, nested loops. O2 circumflex n exponential time. The runtime doubles with each increase in the input size, for example, brute force solutions to some problems. Big O notation helps developers compare the efficiency of different algorithms. Choose the best algorithm for a particular problem. Understand how algorithms will scale as the input size increases. Optimize algorithms for better performance. This is measured in Big O notation, which describes the relationship between growth of input size and number of operations needed to execute the algorithm. For example, adding 1 to every number inside an array is On, because the number of operations increases in a linear way as the array grows. What's relevant is not the exact number of operations, but rather the trend as the input size goes to infinity. You see, something like n grows way faster than any linear function ever could. So as long as the time complexity is some kind of linear relation, it's simplified down to On, and the same thing goes for any other group. Algorithms are fundamental to computer science and are used in various fields, including artificial intelligence, machine learning, and software development. Algorithms can be represented in different ways, including pseudocode, a plain language representation of the algorithm. Flowcharts, diagrams that visually represent the steps of an algorithm. Programming code, algorithms are implemented using programming languages to create software. In essence, algorithms are the recipes that computers follow to solve problems and perform tasks. When writing algorithms, there's some general approaches. For example, when searching an item in a list, a brute force approach would be to simply check every item until we find the target. But a more sophisticated approach would be divide-and-conquer. For example, in binary search, you cut the problem in half each time by checking the middle element of a list and seeing on which side the target is until you land on the target. Now, when solving a problem with code, there's always multiple ways to achieve the same result, which are called programming paradigms. Let's try to find the sum of all elements in this list. Declarative programming describes what the code does, but not how exactly the computer should do it, whereas imperative programming explicitly describes how the computer should achieve a result with detailed instructions. In computer programming, a paradigm is a fundamental style or approach to organizing and implementing computer programs. It's a way of thinking about how to solve problems using code rather than a specific language. Paradigms define the overall method or style of programming, offering different ways to approach problem solving. While specific languages may support or be better suited for certain paradigms, a paradigm isn't tied to a particular language. There are numerous paradigms, each with its strengths and weaknesses for different types of problems. Common programming paradigms. Imperative programming focuses on telling the computer how to execute a series of steps to achieve a result. Procedural programming extends imperative programming by using functions, procedures to organize and modularize the code. Object-oriented programming, OOP, organizes code around objects that contain data and behavior, facilitating modularity and reusability. Functional programming emphasizes the use of functions to build programs, avoiding mutable state and side effects for predictability. Declarative programming describes what should be achieved rather than how, leaving the implementation details to the system. Importance of understanding paradigms. Knowing different paradigms allows you to choose the most appropriate approach for a given problem. Paradigms provide structured ways to organize code, improving readability and maintainability. Language choice. Understanding paradigms helps you evaluate which programming languages are best suited for your needs. Collaboration. A shared understanding of paradigms facilitates collaboration among developers. An extension of imperative programming is object-oriented programming, where you can define classes as blueprints for objects, which are single units consisting of data in the form of properties and behaviors in the form of methods. To code a call, you begin by defining the properties as variables and the methods as functions. After encapsulating properties and methods in a class, you can instantiate an object and use the dot notation to work with its properties and methods. Classes make it easy to organize and reuse code because you can define subclasses that inherit properties and behaviors of a superclass, but can also extend and override them. For example, a rubber duck subclass might implement quack with a squeak instead. As a result, rubber ducks can be treated as objects of the duck class but behave differently when is called, which is the concept of polymorphism. But for some problems, none of these traditional machine learning paradigms will work. Let's say you want to make a computer recognize which of these images is a bee. The problem is you can't really describe what a bee looks like with code. This is where machine learning comes in, aka teaching a computer to do a task without explicitly programming it to do that task. First, you need a lot of data, which you split into training and test data. Next, you choose an algorithm that can change its parameters over time, for example, a neural network, where the weights can be updated to achieve a different result. By feeding lots and lots of training data into this algorithm, you can build a model whose accuracy you can then check with the test data. If it's not quite right, the model can improve over time by comparing the output to what it should have been, capturing the difference in an error function, and tweaking its parameters to minimize the difference. But no matter how futuristic, bleeding edge, blazingly fast, and optimized it is, if you want people to actually use the application you wrote, you should probably know about the internet. It's a network of computers from all around the globe connected by wires. Like literally, the internet is a bunch of thick cables that run at the bottom of the ocean, along with facilities like internet service providers that connect you to your destination. The internet is a global network of interconnected computer networks that allows for communication and information sharing between devices worldwide. It's a system of systems where any computer connected to it can communicate with any other. given they are both on the internet. The internet is not a single centralized network, but rather a vast collection of smaller networks like those within a school, company, or home that are all connected to each other. This means that data can flow freely between these smaller networks, allowing computers on one network to communicate with computers on any other network connected to the internet. The internet facilitates various forms of communication, including email, chat, video conferencing, and file sharing. It also provides access to a vast amount of information through the World Wide Web, WWW, where websites and web pages are stored and can be accessed by users. Individuals and organizations gain access to the internet through ISPs, which provide the connection between their devices and the larger network. While often used interchangeably, the internet is the underlying network infrastructure, while the WWW is a specific service that uses the internet to distribute information in the form of web pages and websites. These computers communicate with the Internet Protocol Suite. Every computer on the network has a unique IP address. Two computers can then transfer data with the Transmission Control Protocol. It breaks messages into a bunch of packets, sends them through a network of wires before the receiving end puts the message back together. If you have a poor internet connection, you might have experienced packet loss, which is just if some of these packets get lost along the way. In the world of computing, the Internet Protocol, IP, is a set of rules that governs how data is formatted and transmitted over the internet and local networks. Essentially, it's the communication language of the internet, enabling devices to send and receive data across the network. IP addresses, numerical labels assigned to devices, are a key part of this process, facilitating communication between devices. IP dictates how data is broken down into packets, which are then sent across the network. Each packet includes information about its source and destination IP addresses. IP uses IP addresses to route data packets across networks and through routers, ensuring they reach the intended destination. IP addresses are used to identify devices on a network, enabling them to communicate with each other. There are different types of IP addresses, including public and private addresses, and those reserved for specific purposes, such as loopback and default network addresses according to Fortinet. IP is part of the broader TCP/IP protocol suite, which also includes protocols like TCP and UDP, which handle data transmission at the transport layer. TCP, for example, guarantees reliable data delivery by ensuring packets are received in order, while UDP is a faster, less reliable option. There are different versions of IP, including IPv4 and IPv6, with IPv6 offering a larger address space and improvements in routing. IP forms the foundation of the internet, providing the addressing and routing mechanisms that allow devices to communicate across the vast network. If the internet is the hardware, then the web is the software, which you can use with a browser. Every page on the web has a URL. When you type it into your browser, it looks up the IP address of the server hosting this website with the domain name system, which is like a mapping domain to IP addresses of actual servers. After connecting to it via TCP, your browser, called the client, uses the Hypertext Transfer Protocol to send an HTTP request to the server, which then gives a response, ideally containing the contents of the web page. The World Wide Web, WWW, or simply the web, is a system of interconnected documents accessible through the internet. It's a global information space where users can access various websites, documents, and other digital resources. The web is built upon key technologies like HTML for structuring web pages, HTTP for communication between web servers and browsers, and URLs for locating resources, according to Britannica. The web is a collection of web pages, images, videos, and other digital content linked together through hyperlinks. You need an internet connection to access the web and browse its vast network of resources. HTML, Hypertext Markup Language, defines the structure and content of a web page. HTTP, Hypertext Transfer Protocol, establishes communication between web browsers and servers. URL, Uniform Resource Locator, a unique address for each web resource, allowing users to navigate to specific locations. The WWW was invented in 1989 by Tim Berners-Lee at CERN, a European scientific organization. It was originally designed to facilitate information sharing among scientists. the web has since evolved into the global phenomenon it is today. HTTP stands for Hypertext Transfer Protocol, and it's the foundation of communication on the World Wide Web. It's a set of rules that define how information like web pages is exchanged between a web browser, client, and a web server. Essentially, it's the language that allows you to browse the internet and access websites. HTTP operates on a client-server model, where a client, like your browser, sends a request to a server, and the server responds with the requested information such as the HTML, CSS, and JavaScript for a web page. HTTP is the core protocol for the World Wide Web, allowing users to navigate and access web content. HTTP builds upon the Transmission Control Protocol, Internet Protocol, TCP/IP suite, providing the reliable and structured communication necessary for internet traffic. Hypertext refers to text that contains links to other documents or resources, allowing users to navigate between different pages and websites. While HTTP is the basic protocol for web communication, it's important to note that HTTP is not secure. HTTPS, Hypertext Transfer Protocol Secure, uses encryption to protect the data transmitted, making it a more secure protocol for sensitive information such as login details or financial transactions. HTML, CSS, JavaScript. The actual website most often consists of 3 parts. An HTML file contains all the content of a website and is basically just a collection of elements, which can be text, links, buttons, and so on. A CSS file controls the visuals and makes a website look nice. But a website is useless if pressing nice-looking buttons does nothing, so a language like JavaScript adds functionality. But sometimes things can go wrong. With every HTTP response comes a response code which carries information about the status of the response. For example, 200 means OK, and anything starting with 4 is an error, the most famous one being 404 page not found. HTTP status codes are 3-digit numbers that a web server sends to a client, like a web browser, to indicate the status of a request. They help determine if a request was successful, redirected, or resulted in an error. For example, a 200 OK status code means the request was successful, while a 404 not found code indicates the requested page could not be found. These codes indicate that the request has been received and is being processed. 2. Success. These codes indicate that the request was successful and the server has completed the request. 200 OK. The request was successful and the server returned the requested data. 201 created. The request was successful and a new resource was created. 204 no content. The request was successful but the server didn't return any data. 3. Text redirection. These codes indicate that the client needs to take additional action to fulfill the request, usually because the resource has moved. 301 moved permanently. The requested resource has been permanently moved to a new location. 302 found. The requested resource is temporarily located at a different URL. 4XX client error. These codes indicate that the client made an error in the request. 400 bad request. The server could not understand the request due to a client error. 401 unauthorized. The client is not authorized to access the requested resource. 403 forbidden. The client is forbidden from accessing the requested resource. 404 not found. The requested resource could not be found. 5. SEX server error. These codes indicate that the server encountered an error while processing the request. 500 internal server error, a generic error indicating a problem on the server. 502 bad gateway. The server received an invalid response from another server it was acting as a gateway for. 503 service unavailable. The server is temporarily unavailable. HTTP requests can carry different methods, for example, get, post, put, and delete, so retrieve, add, update, and delete information. These are often used by application programming interfaces which connect 2 applications and allow them to interact with each other, for example, store and retrieve data from a database. In the context of computers and web development, HTTP methods, also known as HTTP verbs, define the action a client, like a web browser, wants to perform on a resource, like a web page or data, hosted on a server. They are crucial for managing communication between clients and servers over the web. HTTP methods are instructions within an HTTP request that tell the server what type of action the client wants to perform. Common examples include get, to retrieve data, post, to send data to the server, put, to replace an existing resource, and delete, to remove a resource. They enable clients to perform CRUD, create, read, update, delete operations on resources managed by a server. When a client sends a request, the HTTP method specifies what action the client is requesting the server to take. Some methods, like put and delete, can modify the server's state, while others, like get, are considered safe and may not. Some methods are idempotent, meaning that making the same request multiple times has the same effect as making it once. Relational databases and APIs. The most common type of database is a relational database, which uses tables to store data. Columns of a table contain different attributes and rows represent individual data points. Also, each table has one unique attribute called the primary key. A foreign key is the primary key of another table, establishing a relationship between the two. In this case, each book is connected to an author. In the context of computers, SQL stands for Structured Query Language. It's a programming language used to manage and manipulate data stored in relational databases. SQL allows users to perform actions like querying data, creating and modifying database structures, and managing access permissions. SQL is specifically designed for relational databases, which organize data into structured tables with rows and columns, much like a spreadsheet. SQL provides the commands to interact with the database, such as selecting, inserting, updating, and deleting data. SQL is a standardized language, meaning it has a widely accepted syntax and structure across various relational database management systems, RDBMS, like MySQL, PostgreSQL, Oracle, and Microsoft SQL Server. SQL is widely used in various applications, from web databases to enterprise applications, because it provides a powerful and flexible way to manage data. With a language like SQL, you can write statements to work with data from these tables. You could look up the titles and authors of all books whose title starts with H, but for that we have to join the authors table with the books table on the matching key to combine two attributes from different tables into one, giving us this output. These statements are useful, but you've got to be careful or you might just delete an entire database with one line of code, but don't worry, that's never happened before. In computing, SQL injection is a code injection technique used to attack data-driven applications, in which malicious SQL statements are inserted into an entry field for execution, for example, to dump the database contents to the attacker. SQL injection must exploit a security vulnerability in an application software, for example, when user input is either incorrectly filtered for string literal escape characters embedded in SQL statements, or user input is not strongly typed and unexpectedly executed. SQL injection is mostly known as an attack vector for websites, but can be used to attack any type of SQL database. SQL injection attacks allow attackers to spoof identity, tamper with existing data, cause repudiation issues such as voiding transactions or changing balances, allow the complete disclosure of all data on the system, destroy the data or make it otherwise unavailable, and become administrators of the database server. Document-oriented NoSQL databases can also be affected by this security vulnerability. Behind every login page is a database with usernames and passwords. When a user tries to log in, an SQL query is often used to check if the user input matches with an entry in the database. That's good, but a devious actor could type something like this, which changes the query by terminating the string early and commenting out the rest, which means as long as this username exists in the database, access is granted. This is called an SQL injection attack and is one of the easiest ways hackers get places they're not supposed to. In the context of computers, Brilliant often refers to the interactive learning platform Brilliant.org. This platform uses interactive lessons to teach math, data science, and computer science concepts. Brilliant.org aims to make learning these subjects more engaging and effective through its bite-sized lessons, visual aids, and real-time feedback. Hearing about all these concepts is one thing, but to really learn them, you have to see them in action and use them yourself, which is exactly what you can do with Brilliant, which has thousands of interactive lessons for everything from math and data science to programming and AI. They make knowledge stick with visual lessons and interactive problems, which is not only fun and builds intuitive problem-solving skills, but also proven to be 6x more effective than simply watching hours of lectures. I know that making time to learn new skills can be difficult, but Brilliant makes it so easy. You can build valuable knowledge from the ground up in just a couple of minutes a day, with bite-sized lessons from any device, anywhere, anytime. You'll go from the basics of data science to analyzing real data sets from Spotify in absolutely no time, which you can supplement with math fundamentals and programming courses in Python to build one of the most in-demand skill sets of our time. The best part? You can try everything Brilliant has to offer for free for a full 30 days by visiting brilliant.org/wackyscience/. You'll also get 20% off an annual premium subscription. Thanks to Brilliant for sponsoring this video.